So now we're starting the next section out of the book on set theory. Set theory is fundamental to mathematics. All of the math that you've seen throughout your high school and college career, it's all based on the idea of sets. And you've probably seen things like Venn diagrams before. So we're going to formalize some of this, and I suspect that a good bit of this may be brand new to you. So make sure you take notes and try to work through all of the examples. All right, so uh, it's kind of a basic definition. We're just going to say that a set is an unordered collection of objects, and the objects inside the sets are called the elements or the members of that set. Now, a set contains its elements. So, for example, if we have a situation where we have a set called X, and X is going to be the element of it, then A contains X. And this is the notation we use to say that X is an element of A, or that A contains X. And if X is not an element, then this is the notation we use. So we would just use the an element of symbol and then just strike it through the same way we would with a not equal to sign. So just as a quick example, S is going to be the set of states in the United States. New York would be an element of S. Ontario would not be an element of S. So you see, sets aren't just restricted to mathematical things. We can make the set of whatever we want with a few technical caveats that we don't need to worry about. But any unordered collection we want, we can make it into a set. Now, if we take E to be the set of even integers, then 2 is an element of E and 3 is not an element of E. Now, there are different ways that we have to describe and write the elements of a set. One most common one is what's known as the roster method. And all you do is you just list out all of the elements of the set. So for example, this is the set that contains this element, and this element. Now, I want to say a couple of things about sets. We are going to always use curly braces like this to indicate we're talking about a set. And that's going to distinguish it from using parentheses, not the same thing as writing it with parentheses. And it's also not the same thing as using brackets. Okay, we're going to be very, very particular that we're only talking about a set if we use curly braces like this. Okay, now moving on. In Python, we actually do have a data type of set. Okay, so in addition to the data types we talked about before, like integer, float, string, Boolean, we do have a data type of set in Python. And the way that we write it is just with those aforementioned curly braces. So here's a little thing in Python Tutor. I'm going to define the set A to be the set containing these elements. So curly braces and then the roster method. And then we're going to do some print statements to see if A is in there and to see if 0 is in there. So first of all, I'll define A to be this set. So here's my frame, here's my object, here's the set 0, 1, 4, -2. I want to point you something out that's very, very important. And it was part of the definition of a set before. Sets are unordered. Okay? And that distinguishes them as a data type from lists in Python. Remember, lists always have an associated index. That's not true with sets. Notice how I entered my set -2, 0, 1, and 4, but Python saved it as 0, 1, 4, -2. Sets are unordered. That is, if I write the set -2, 0, 1, and 4, that is the exact same set as writing 0, 1, 4, and -2. Those are identical. Those are the same sets. Order doesn't matter. Something else just to let you know about in sets, repeats don't matter. That is, if I write the set -2, 0, 1, and 4, that is the same set as writing -2, 0, 0, 1, 1, 1, 1, 1, 4, 4. And I could get even more ridiculous with it. Because the zeros and the ones and the fours are repeated, those are the same sets. And we'll talk about that a little bit more when we get into what we mean by sets being equal. All right, now let me get rid of all this and then go through this Python tutor code. So we've defined A to be this set, -2, 0, 1, and 4. And then now I'm going to print the result of 5 in A. So the result of 5 in A, well, that's either true or false. So the result is going to be a Boolean. Since 5 is not an element of my set, that's going to print out false. And now I'm going to print out this Boolean, 0 in A. Well, 0 is in my set. That's going to print true. All right. You can also print or list the elements of a set in Python using this code snippet, which I'm not going to go through, but I encourage you to do it on your own. And I want to move on to something called set builder notation. So you're probably familiar with this from college algebra or calculus if you've had it. And this is a way to describe a set without listing all of them out. And it consists of two different parts. We, first of all, say the set of all x in some domain. So this is going to be where all of our elements come from. This is kind of like the big overarching thing where the elements come from. And then we're going to have some predicate. So writing curly braces x in D, and this colon, this is read such that, and sometimes you'll see this written like this, x in D, and instead of writing a colon for such that, we'll use a vertical line. But they both mean the same thing, and it's good to be a little bit flexible with your notation, because if you look at other resources or even other textbooks for college algebra or calculus, they may use the colon, they may use the line. So they both mean the same thing. All right, so here's an example. Consider this set. All x in Z, where this is the integers, and we'll talk about all of these sets a little bit later, but the integers, you'll recall, consists of 0, 1, 2, goes on forever, -1, -2, that goes on forever. So all x in Z such that -2 is less than or equal to x is strictly less than 4. Well, we could write this in the roster method just by listing all of the x's that satisfy those conditions. So x has to be greater than or equal to -2. So we start listing -2, -1, 0, and x has to be strictly smaller than 4. So we'll keep going until we get up to 3. And now since we're only using integers, remember, we're not using fractions or anything like that. That's all. So these two sets are the same set. We're just writing them different ways. One with the set builder notation and one with the roster method. So there's a you try here that I encourage you to try. But I'm going to do just a couple of them. So let's rewrite this one in set builder notation. Well, this is every integer so that when you square it, you get 1. Well, what numbers does that work with? -1 squared and 1, that's all. So notice that this one matches with this one down here. Okay, let's look at one more. This is going to be all of the integers so that their square is strictly less than 4. Well, 2 doesn't work because 2 squared is equal to 4. 1 works because 1 squared is 1. 0 works. And -1 works because -1 squared is going to be strictly less than 4. So that one is going to match with this one, and so on and so forth. And I encourage you to try these out. This one is a lot of fun. Just a little note, whenever you, like I did before, whenever you can't list out every element of a set, you can use ellipses to indicate that it goes on and on forever like that. Okay, this is a nice little Python exercise that I would like you to try. because there's an interesting there's an interesting use of this for and conditional right there. So this would be something for you to investigate and try to understand on your own how that's working and why that works the way that it does. So go ahead and take a look at that when you have time. Okay. Here are some special sets of numbers along with the notation we use for them. It'd be good to be familiar with these, but I'm not going to ask you to memorize them. If they ever show up and you forget how to use them, just, you can look them up or ask or something. Like I said before, this double bar Z, and we usually write it like this if you're using handwritten. Just to make sure there's 2 bars there. That's the integers. If we write double bar Z plus or an N, this is how we usually write that. That's what's called the natural numbers or the positive integers. So it's 1, 2, 3, and so on. Here, this Q, the way we write this one by hand is usually like this. This is the rational numbers. And so it's basically all fractions where the numerator and denominator are integers. But remember, you can't divide by 0. So we have this additional restriction right there. It's the rational numbers. Then we have the real numbers. By hand, it's written like that. R plus is a set of positive real numbers. Here we have the complex numbers, by hand written like this. So the complex numbers are anything that can be written like this: a plus I times b, where a and b are any real numbers, and b is not equal to 0, and I is defined to be the square root of -1. Another way we can write that is I is defined to be such that I squared is equal to -1. We're not going to use the complex numbers. I just wanted to show you that notation. And we'll come back and revisit this when we talk about subsets. Now, moving on. We'll need some other special sets, one of which is known as the empty set. The empty set ends up being very, very important for lots of reasons in mathematics, but it is the set that contains no elements. So for example, think about this right here. The set of all integers such that x squared is equal to 2. Well, this equation, x squared equals 2, you can't solve that and still have an integer, because if you take square roots of both sides, you're going to get x equals plus or minus root 2. And the square root of 2, that is not an integer. So this set that I'm trying to describe in set builder notation, this has no elements. It's the set with no elements, and it's called the empty set. One way we denote that is just with the curly braces, but nothing inside. Another way is a 0 with a strike through it. Okay. Now, some people like to use the circle with a strike through it to mean the number 0. Stop doing that, because in mathematics, that's the empty set. Another Python tutor exercise that I encourage you to work through on your own, and you can ask me questions about it if you need to. One idea that it's important to know about is what's called cardinality. And simply put, cardinality is simply the number of elements in the set. Now, this is a discrete math class, so most of the time we're only thinking about finitely many elements of a set, okay? And we denote it by what looks like an absolute value sign. So for example, this set right here, the set 0, 1, 2 has 3 elements. And so when we put the absolute value symbols around it, the cardinality is 3. However, the integers is an infinite set. So we say that its cardinality is infinity. And also the cardinality of the empty set is 0 because it contains no elements. So just remember, what does cardinality mean? It's the number of elements in the set. And the last thing to talk about in this video is what it means for 2 sets to be equal. So by definition, 2 sets are equal if and only if they contain exactly the same elements. So this is why repetition doesn't matter, like I mentioned above, okay? When two sets are equal, we write it with an equal sign. When they're not, we write it with a not equal sign. So that also explains why order doesn't matter for sets. Because if you think about the set 2, 3, 5 and the set 5, 2, 3, they contain exactly the same elements, and so they're equal. Similarly, thinking about these two sets, well, A is in the left set, A is also in the right set, B is in the left set, B is in the right set, C is in the left set, C is in the right set. But look, all of these ones that are repeated, I've already covered them, right? C, we already know that C is in the left-hand set. So these two contain exactly the same elements, which makes them equal as sets. All right, so before I move on to the examples for this chapter, for this section, I want to look at the notes. And again, I always encourage you to read through these notes because it summarizes the information. So here we're talking about sets and elements and members with these examples, roster and set builder notation. But don't forget, I have these embedded example videos for you to watch that work things out in the roster method and set builder notation. So read through this, look at the examples. There's one additional piece of information that's in this set of notes that's later in the book, and that's the universal set. And the universal set is just the set of everything under consideration. And I'll talk in more detail about that just a little bit later. Let's look at some example problems. So what I want to do is to just do these two problems, or some selections from these two problems. So I took number 3 from the first set of notes from the practice problems, and I want to describe the following sets using the roster method. So here I have the set that contains everything of the form 3n plus 1 such that n is a natural number. Now notice that this is reversed of the way that it was written in the textbook, and that's done on purpose because you need to be a little bit flexible. Things can be written like this as well. This is especially useful when you are writing something in the roster method because you can just say, well, I'm looking at the natural numbers and I'm plugging them in to that expression. So what am I going to get? If n is equal to 1, I'm going to get 3 times 1 plus 1. If n is equal to 2, 3 times 2 plus 1, 3 times 3 plus 1, and so on. So that is, I'm going to get 3 plus 1 is 4, 6 plus 1 is 7, 9 plus 1 is 10. So look what I'm doing. I'm just adding 3 to all of these numbers. Okay. And so that is how you would write that set using the roster method. Now, for this one, for the next one over here, the set of all integers such that when you square them, you get something less than or equal to 4. Well, 2 squared is equal to 4, but 3 squared is bigger than 4. So 2 is the biggest number that I could have inside there, which that also means that negative 2 is the smallest. Negative 1 squared is 1, that works. 0 squared is 0, 1 squared works. 2 squared I've already said is 4, 3 squared is 9, that's too big, and so that's it. So those two sets are equal. Set builder notation and the roster method of writing out the elements of the set. Okay, moving on to the next problem. Whoops. Assume the universal set is a set of integers. So the only thing we care about right now are integers. And I'm defining 4 different sets here. Now, in the practice problems, there are more than just this one listed out. Is the set A equal to B? But this is the only one we're going to do. Remember what equal means for sets. They have exactly the same elements. Well, this is listed out in roster method, so it's kind of easy to see what's going on. This one is not listed in roster method. So why don't we do that? Why don't we write out what B is using the roster method? So B is equal to the set of all integers such that x squared is equal to 4 or x squared is equal to 9. So that's equal to, Well, what numbers are integers such that when you square them, you get 4? There are only 2 of them, -2 and 2. And then what numbers are such that when you square them, you get 9? -3 and 3. So that is B in the roster method. What does it mean for 2 sets to be equal? They have exactly the same elements. So here, -3 is in A, -3 is in B, -2 is in A, -2 is in B, 2 is in both of them, 3 is in both of them, and that's all of the elements that's in either one of the sets. So that tells us, since they have exactly the same elements, A is equal to B. So that's all for this video. Please practice the example problems, and then you can move on to the next video in the list.